Hello everyone, I hope I am audible and let's start today's tutorial session. This is tutorial 6 of the Measure and Integration NPTEL course. So tutorial 6, Measure and Integrations NPTEL MA 68 and today's date is 30th August. Okay, so in today's session mainly we will be focusing on the dominated convergence theorem, monotone convergence theorem, and um, and applications of those basically. Okay, so whenever a sequence of measurable integrable functions converges to an integrable functions, when the integration is also converges, that is what we will be focusing on today, and what are the conditions one can apply, one can use, and prove those things. Okay, these are the things basically we will be focusing. So let's start solving a problem, and during the during solving this problem, we will be stating the theorems whatever is needed for that time. Okay. So first problem. So okay. So let me write then two important theorem: um, monotone convergence theorem and dominated convergence theorem. So before that, let let x um, S mu be a measure space, and f is a function from x to c be a measurable function, complex valued function, measurable function. Okay, then that means inverse image of every open set is actually inside this sigma algebra. So then f is called measurable function. So f is actually measurable functions. If inverse image of every open set is contained in this sigma algebra, then f is called measurable function. Okay, and if it be a measurable function, so in that case, first of all, be a okay. So we say if integration of a mod x mod of f d mu is finite, then we say f is integrable. Okay, note that mod f is an extended real valued non-negative definite extended real valued non-negative valued function. So therefore, there is a definition of a whenever f is, suppose g is a function from x to c, such that g is extended real value, that is g is the function from 0 to infinity, that means g can take value infinity as well, and g is greater than equals to 0. So in that case, there is under the integration of gx d mu, this is given by like this way: supremum 0 less than phi less than equals to g, and phi are simple function. If here phi is simple measurable functions, then these are the, and for that simple measurable functions, you know how to define this one. Suppose phi is a simple measurable functions, phi is given by some alpha I, characteristics function ai equals to 1 to n. This ai are the measurable. So in that case, phi d mu is actually given by phi d mu over x, actually given by summation of ai and measure of ai. So this is what for a simple measurable functions, a function phi is said to be simple if it is written like this way: phi is equals to summation of ai, characteristics function of capital AI, where I equals to summation of alpha characteristic function of ai. Here ai are the measurable sets. So then simple function is said to be measurable, and for a simple measurable function, the integration is actually defined by, this is the way it is defined. Okay, so this is the way it is defined, and so this is how it is defined for simple measurable functions, and for an extended real valued measurable functions, the integration is actually given by this. So therefore, here mod of fh is an extended real valued function. So we can give the, we know what is mean by this particular things. Okay, and so so then if we have this particular thing, then we say f is integrable, and if f is equals to u plus iv, where I and where u and v, are real valued function, where u and v where u and v are real valued function, then integration of f d mu is equals to integration of u d mu plus integration of v I d mu. Where note that here we know that if we know if a function is positive extended real valued function, non-negative extended real valued function. So in that case, we know how to define this. Now, if a function is not extended real valued, but rather than it is just only real valued, okay. So in that case, how to define the integration of g d mu? In that case, it will be g plus d mu minus g minus d mu, where g plus is the maximum of g and g minus is the minimum of g. Okay, so this is the way one can give the definition. Okay, so this is the definition of measurable function. So with this definition, so monotone convergence theorem says that monotone convergence theorem, what it says, let x s mu be a measure space and fn l equals to 1 to infinity be a sequence of non-negative integrable functions sequence of non-negative integrable functions on x such that for every x in this capital set capital X, 0 less than equals to f1x less than equals to f2x. So this is what it is saying, the monotone convergence. Okay, fnx less than equals to this, and this will hold. And second condition is that limit n tends to infinity, this fnx converges to the function f of x. Okay, if we have these two conditions, then limit n tends to infinity, integration fn x d mu is equals to integration x f d mu. So this is the monotone convergence theorem. And another theorem is the dominated convergence theorem. So let me write that one, dominated convergence theorem, and after that we will start to solving problem. These are the two famous theorem and very important theorem as well. Convergence. I think this dominated convergence theorem is the most important theorem of the major theory course. So Monotone Convergence Theorem says let X S mu be a measure space and let Fn be a sequence of non-negative, sorry, there is non-negative is not needed, the sequence of complex valued integrable function defined on X. Okay. Converging pointwise almost everywhere to a function F. Okay. So here this is the assumption that XS mu be the measure space and Fn be a sequence of complex valued function and they are integrable functions. Okay, and they converges almost everywhere pointwise to F another function F. Okay, and this is the assume further that for any n belongs to for any um, x belongs to capital X and n belongs to capital natural number n, we have mod of fn x less than equals to gx, where g is a non-negative integrable function. Integrable function defined on x, then f is integrable. This is the first outcome. Further, limit n tends to infinity integration over x mod of fn minus f dmu equals to 0. In particular, we have limit n tends to infinity integration fn dmu is equals to x f dmu. Okay. So here what we have said, there is two things. First of all, the assumption. That uh, assumption says that these things and that x is the measure space and fn is a sequence of integrable functions. These two are the assumptions. Now, if I and which converges pointwise almost everywhere to another function f. Now, if I want to prove that integration of fn converges to integration of f, we first need that f has to be integrable. First point. Second point is that integration of fn has to converge to f. So for that, we will be trying to find another function g non-negative integrable function on x such that mod of fn x less than equals to gx for all x belongs to x and all n belongs to natural number. So that means fn is bounded by another function. If all the fn's are bounded by another function, so then in that case, if we are able to find this type of conditions, this g we are able to find an integrable function g with these conditions, then we can say that f is integrable. First outcome is f is integrable. Second outcome is that limit n tends to infinity integration over x mod of f and f minus f dv equals to 0, which in particular gives this condition. Okay. So now let's go to the first problem. It may look that there must exist many similarities between the Monotone Convergence Theorem and Dominated Convergence Theorem, but both they are not same. Okay, they are not same. First of all, in dominated monotone convergence theorem, we have considered only non-negative extended real valued functions. Okay, so they are always integrable. Their integration functions value can be infinity. So they are always integrable. There is no doubt. But if we consider a complex valued function, then that can be integrable. That can fail to be an integrable function. Okay. Okay. So let's write the first problem. Problem one. Let x s mu be a measure space. Let fn n equals to 1 to infinity be a sequence of measurable functions defined on x converging converging to a measurable function if almost everywhere. So this convergence is pointwise. Okay, assume that f1 greater than equals to f2 greater than equals to fn greater than equals to all the way greater than equals to 0. That means all the functions are positive value, first place, and second place is that f1 has decreasing value, decreasing, okay, at each point. And that f1, only one function it is saying that f1 is integrable. Okay, integrable. So that limit n tends to infinity integration fn d mu x is equals to integration x f d mu. Okay, so here we can do two things. First of all, we can use the dominated convergence theorem where we don't need this one. Okay, if I want to use dominated convergence theorem, then we don't need is greater than 0. So let's try using the dominated convergence theorem. So using dominated convergence theorem, using DCT, dominated convergence theorem. So we will write here it is DCT, dominated convergence theorem, and monotone convergence theorem as MCT. Okay, so using DCT, what it says. So note that fn is less than equals to f1. Okay, that is true. That means, and no, there is also needed 0. So that means mod of fn is less than equals to mod of f1, okay, for all n belongs to natural number, because this is happening because positive, both of them are positive valued. So both of them are non-negative valued. As both of them are non-negative valued, fn less than equals to f1 implies that mod of fn less than equals to mod of fn. So basically they are positive value. Their mod is actually nothing, not making any difference. That is still it is same. So that implies that as f1 is integrable, then fn's are integrable for all n belongs to natural number. Okay, so this is what first things. So now note that, and extra point, fn's of x, this is less than equals to f1x for all x belongs to the set x and n belongs to natural number. So now this is playing the role of g in the dominated convergence theorem. So as this is playing the role of G in the dominated convergence theorem, so here it is satisfying all the conditions of the dominated convergence theorem, and moreover, so that implies then by using dominated convergence theorem, the pointwise limit, almost everywhere pointwise limit, f is integrable first place, and limit n tends to infinity integration fn d mu over x is equals to integration x d mu. But one can do using the monotone convergence theorem as well. So let's write using monotone convergence theorem. Using MCT. Consider Gn which is equals to f1 minus fn for all n belongs to natural number. Then note that f of n is less than greater than equals to f of n plus 1. That implies f1 minus fn is less than equals to f1 minus fn plus 1 for all n belongs to natural number. So this gives that g of n is less than equals to g of n plus 1 for all n belongs to natural number. So this gives that gn is actually, and also Gn is positive value because f1 is always greater than fn. Okay, so that Gn be a sequence of non-negative real valued. Here I think real valued because we have not considered fn be and sequence of measurable functions defined as converging to a. Okay, so this is real valued, extended real valued. It can be non-negative extended real valued measurable functions, extended real valued measurable functions, and Gn converges to f1 minus f. That's true. There is no doubt. Okay. As n tends to infinity, almost everywhere, pointwise, everywhere. Okay. That implies by using, now we can use the monotone convergence theorem on the sequence Ga. So integration x limit n tends to infinity Gn d mu is equals to integration x f1 minus f d mu, which is equals to integration x f1 minus d mu minus integration x f d mu, and the left hand side will change to that integration x f1 d mu minus limit n tends to infinity integration x fn d mu. So this gives that integration, this gives that limit n tends to infinity integration x fn d mu is equals to integration x f d mu. So this completes the proof. So both using dominated convergence theorem and monotone convergence theorem, we can prove this particular problem. Okay. Now let's then try to the another problem. So I'll take a little short break. So let's try to do solve another problem. let x s mu be a measure space such that mu of x is finite. That means mu of x is finite. That is finite measure basically. Let n equals to 1 to infinity be a sequence of um, integrable functions defined on x, obviously, converging uniformly to a function f on x, so that limit n tends to infinity fn d mu is equals to integration f d mu. So this is sometimes called uniform convergence theorem, or one can short, but this is not much of use, because this here we are assuming the condition that converges uniformly, which is very strong assumption on a sequence one can have. So these are not in general happen. So that's why this theorem or this is also theorem, but this type of things are not much appears. Okay. So but still it can appear and one can solve it easily. So here is we have many extra assumption that sequence is not only converges pointwise but converges uniformly. But note that here we have assumed the sequence converges uniformly, and with that assumption we also dropped one more thing. I mean, here is the sequence fn is, we have also with that assumption also another assumption is that mu x is finite. Okay. So mu x is finite and sequence converges assumption. This is the two extra assumptions we have considered instead of the other fact that fn converges point twice to a. But also we have dropped one more fact that there was, if I want to use the dominated convergence theorem, then there should exist a g such that mod of f of nx should satisfy this condition for all x belongs to x, and g has to be integral. So this condition is not here. And monotone convergence theorem, the monotonicity that we are not assuming here. So therefore we also dropped some condition but also assumed some more condition. Okay. So therefore let's check how this happens. Okay. Now first thing is that as the sequence converges uniformly, so enough to prove that limit n tends to infinity enough to prove that limit n tends to infinity integration x mod of f minus f d mu is equals to 0. That is, for any given epsilon greater than 0, there exists a natural number n naught belongs to the natural number such that integration x mod of f minus f d mu is less than epsilon for all n greater than or equals to this natural number n naught. Okay, so this is what we have to prove. But here we have used the fact that this measure is finite. This is very much strong thing which are assuming. So note that here we are assuming measure is finite, not the sigma finite. Sigma finite is the measure which can be written as a countable union of some measurable sets, where each of the element of that countable union is finite as having finite measure. So that is sigma finite measure. So here we are considering finite measure. Even if we drop this finite measure assumption to the sigma finite measure assumption, still the uniform convergence theorem does not going to help anything. So we will be discussing one problem. So this is the thing. So so let's try then. It is known that it is given that that f is fn is uniformly converges, fn converges to f, fn converges to f uniformly. Then for epsilon greater than 0, there exists a natural number n naught such that mod of f of nx minus f of ax, this is always less than epsilon for all x belongs to the set x and for all n belongs to n naught. We will choose the same n naught and same epsilon. For the given epsilon, we will choose the same n naught. Then integration mod of f of nx minus f of x d mu x, this is less than equals to integration epsilon x d mu, which is, this is strictly less than, this is less than, which is equals to epsilon into measure of the set x, but this is finite. Okay, so that means one can choose epsilon dashed here, epsilon dashed here, epsilon dashed here, epsilon dashed here, that is less than epsilon. So one can choose that epsilon, or one can choose that this is equals to epsilon, where epsilon dashed has been chosen in such a way where epsilon dashed is equals to epsilon dashed, epsilon dashed is chosen such a way, is chosen for given epsilon such that epsilon dashed mu of x is equals to epsilon. So that means we are done then for all n belongs to natural number. So what it is says that for every epsilon greater than 0, we have to find an n naught which satisfies this condition, right? So this is what we have to do. Now for the given epsilon greater than 0, we have chosen epsilon dashed, that is given by epsilon dashed is equals to epsilon by mu x. Now as fn converges uniformly to f, then for this epsilon dash greater than 0, we will be always getting an n naught such that mod of fnx minus fx less than epsilon dash. Now we will be having this one, so this will done the job. Okay, so this completes the proof. Okay, let's go. Let's okay. So here is one more thing. So one can write here remark, if we draw the condition then above result may fail. In fact, if we replace by the fact that by the assumption mu is sigma finite, still the above result, still the above fail, still the above result may fail. Why? So why this may happen? Okay, so let's give an example. Let us consider fn is a sequence of functions. Let us consider the set x is equals to the natural number set. Okay, and s is actually measurable sets, that is the singleton sets and their union, and and mu is counting measure on this S is equals to the power set, the all collection of all subsets of the natural number n basically. Okay, so that means here it is giving the counting measure, mu is giving the counting measure. Then if you consider fn from this x to real number, complex number, whatever it is, such that fn of k is equals to 1 by n for all k, whenever k is an integer, k obviously integer because k is defining on, we are defining the function fn on natural number. So this is less than equals to and 0 if k is greater than n. K is greater than n. So then fn converges to 0 uniformly. Okay, fn converges uniformly, but integration over fn d mu, that is equals to 1 by n into counting measure of the set 1 to up to n, which is equals to n. This is equals to 1 for all n belongs to natural number. So that means, that is integration over fn d mu does not converges to the 0, which is actually integration over x of f d mu. This does not happen. So therefore this above result fails here. Note that here measure mu is actually sigma finite measure, because the natural number n can be written as the countable union of the integers. That's all, positive integers. So therefore, but each of them have finite measure, and that is the finite measure one. So that means the above theorem. Note that here n is sigma finite. Note that here mu is not finite, rather it is sigma finite. Rather it is sigma, instead it is sigma finite. Okay, so this will settle this issue. So let's solve another problem. So I'll take a little break then. So let if is from R to R. Okay, if is from R to R be a real valued function defined on real value, be integrable. Let T belongs to R be fixed. Okay. Define g of f equals to f of x plus t, where x belongs to real number. Okay. If closed interval AB is subset of R, is an interval so that integration AB G dm1, m1 is the usual Lebesgue measure on real line. Okay, integration a plus t b plus t f dm1. So this is actually the translation property we are looking at. You know that the in class 12 we have done this actually, change of variable basically. Okay, This is, I mean, suppose we have an integration limit from a to b, and you are changing variable x to x plus t or x plus t to x. So in that case, it is happens. So basically, this is the thing in that suppose a to b, we have f of x plus t dm1x, right? So let's x plus t is equals to u. Okay, so in that case, dx is equals to du. So and the range will change to a plus t to b plus t. This is what, and f of u du, something like this. So this is what here it is. Here it is, but in Lebesgue measure it is asking for to do. Okay, so we will do this for first simple function. Okay, first of all, we will do, okay. If I want to show this, first of all, it will be enough to showing it is for a positive function, because if the function is real valued, so it can be written as a plus minus of f minus. So it is enough to showing for a positive value. Now for a positive valued function, it is enough to showing, if I want to prove it for positive valued function, then it is enough to showing for a simple function. And for to prove it for simple function, it is enough to showing for a characteristic function. So let's take the characteristic function. Let E subset of R be a measurable set. Measurable set. Consider let f is equals to characteristic function E. Then g of x, that is equals to f of x plus t, that will be equals to 1 if x plus t belongs to E, and 0 if if x plus t does not belongs to E. So that is x belongs to E minus t, x belongs to E, x does not belongs to E minus t. This is the thing. So that means this is actually the characteristics function on E minus t. This is the set. Okay. So now then integration of g of x over the set x d mu, that is dm1 basically, dm1, that is equals to integration x characteristics function e minus t dm1, that is equals to, okay, x is equals to, x equals to ab here, not the full one. This is equals to measure of the set ab intersection e minus t. And this set measure of this set is actually same with the measure of m1 intersection a plus t b plus t intersection e. This is same because measure is translation invariant, that we know. Measure is translation invariant, that we know. M1 is translation invariant. So that means this can be written as a plus t2 b plus t characteristic function e d mu, that is equals to integration f. So as this is true for a characteristic function, this fact is then true for a simple function. Okay, for simple function this is true. Then that is simple function f or phi f, that's okay. Integration over a to b g, or one can write it as f of x plus t b mu x is equals to integration a plus t to b plus t f of x b mu x. Okay, then for any non-negative, then for any non-negative extended real valued function fn, if there exists there exists a sequence of simple measurable function, simple measurable non-negative functions phi n equals to 1 to infinity, such that phi n converges to and monotonically increasing sequence. One can write a sequence fn of simple non-negative monotonically increasing everything one can do. Sequence phi n equals to 1 to infinity. There exists a sequence of simple non-negative measurable simple measurable functions, such that phi nx is less than equals to phi n plus 1x for all x belongs to x, and for all n belongs to natural number, and limit n tends to infinity phi n is equals to f. Okay, this is what we can give. Then using monotone convergence theorem, then and that implies corresponding the function gn is also going to be that means phi n of x plus t that is equals to f of x plus t that is equals to g, and that is equals to limit n tends to infinity gn. Okay, gn of x, where gnx is equals to phi n x plus t. T is fixed throughout the this question. Okay, so therefore by monotone convergence theorem, integration of g b mu ab is equals to limit n tends to infinity integration of ab g nx. Okay, so now as the above fact is true for the function pn, so this can be written as limit n tends to infinity, just a minute, g of x, limit n tends to infinity integration, as a gnx is equals to pnxt. So that means as pnxt, if this is true for simple function pn, so that means one can write it a plus t comma b plus t f, because this is phi n of x plus t, so this will be phi n. Okay, phi n of x d mu x, so I can write it as clearly. So this can be written as, now phi n converges to x, so therefore one can write it as limit, and limit can be removed. Now using again the monotone convergence theorem, what we get actually integration a plus t b plus t f x d mu x. So this is true for a function. So now using this, now as any function f from real to number to real number, the the result is true. Result is true for arbitrary measurable. True for arbitrary measurable function say. Measurable functions. So this is true. So this completes the proof basically. Okay. So now let's try to do another problem. So I'll take a little break. Okay. So let f from 0 1 to r be a Lebesgue measurable functions. Lebesgue measurable functions be a measurable functions. Lebesgue Lebesgue measurable functions for each fixed t and let g 0 1 to r be an integrable function assume that for each xt belongs to 0 1 times 0 1 mod of fxt less than equals to gx if limit t tends to 0 f of xt is equals to hx so that limit t tends to 0 integration 0 1 f of xt dm1x is equals to integration 0 1 h dm1. Okay, so what it says, first of all it says that f is a two variable function. Okay, and for each fixed t, I mean for the second variable, for each fixed second variable the function is measurable with respect to the first variable, and g is another function. Okay, and that is also integrable. Okay, also it is known that mod of fxt less than equals to mod of gx for all x, and for each fixed t this is what happens. Okay, if limit t tends to 0 fxt is equals to hx so that this happens. Okay, so here we have to use the dominated convergence theorem. Let Tn be a sequence in 0 to 1 such that Tn converges to 0. Okay. Then for each fixed Tn, then for each fixed Tn, consider Fn from 0 1 to the what is real value, how it is given, f of n x is equals to f of x tn. So this is what it is. For each fixed tn, we are defining a function fn. Moreover, this function will converge. Moreover, this fn converges to the function f pointwise. No, I mean basically, moreover, fn x, I mean fn x, that is for tn, fn x converges to f of x comma 0 pointwise. Okay, yeah, and f of nx, this mod is less than equals to gx, where g is integrable. So we have all the weapons to use the um, dominated convergence theorem. So because fn is a measurable function first of all, and that is measurable functions of x for each fixed t, and that will be integrable because g is integrable. That's why the fn will be integrable. So fn is a sequence of integrable function that converges pointwise to the function f. Okay, so therefore g f will be integrable with this. I mean first of all this f as a function of real number 0 1 0 1 to function, that will be integrable. So that means, but okay, sorry, this is the function not fx, this is actually 0 As t tends to 0, this is hx basically. This is given. Note that this is given. Because it is given that limit at t tends to 0, f of x t is equals to hx. So therefore, by dominant convergence theorem, limit n tends to infinity integration over x f of nx d mu is equals to integration over x hx d. So this is the measurable m1 m1 at x. Okay, I can remove the x here because here it is the same thing. Okay, so this is the what it is. But note that as n tends to infinity, Tn tends to 0, right? But note that as n tends to infinity, Tn tends to 0, then above equality is equivalent to integration limit t tends to 0 x f of xt dm1x that is equals to integration x h dm1. Okay, so this is all. This is all. Yeah, so this completes the proof. Okay, so I'll take little time. After that, I will come back to the new problem. Okay, so let's do another problem. This is problem number 4. No, problem number 5. Let, this is very big problem. Let f from 0, 1, 0, 1 to r be a function such that be a same conditions function such that for each fixed t belongs to 0, 1, x goes to f of xt integrable and for each x belongs to 0, 1, the map t goes to f of xt is differentiable. and that the derivative del f del t xt is uniformly bounded. Now it is asked to show that d dt integration 0 1 f of xt dm1x is equals to integration 0 1 del f del t xt del dm1x. So question, it is asked that let f from 0 1 times 0 1 to r be a function such that for each fixed t belongs to 0 1 x goes to f of xt is a integrable, and for each x belongs to 0 1 the map t goes to f of xt is differentiable. So that means in first variable it is integrable, in the second variable it is differentiable. Then the derivative del f, then the derivative del f, then the derivative del f del t is also, it is known that the derivative del f del t xt is uniformly bounded. Okay, then so that we have to show this one. Okay, so let's do this one. So what is mean by this particular thing? So this particular thing, so let's try to, so this is derivative, actually derivative of this particular thing. So so let's write then. Okay, so this is right now function of t only. So that means the derivative means one can know that limit h tends to 0. If I write this is as the f of, so let me write this one. Let f of a t is equals to, let f of t is equals to 0 1 f of xt dm1 x for all t belongs to 0 to 1, close interval. Okay, so now f of t is equals to written by this. Then d dt f of t means limit h tends to 0 f of t plus h minus f of t by h. This is what. So let's first calculate this one. F of t plus h minus f of t by h, which is equals to integration 0 to 1 f of x t plus h minus f of xt by h dm1x. And now by MVT, mean value theorem, this particular thing is actually can be written as 0 to 1 del f del t f of x comma t plus theta h dm1x. So here we have used MVT, mean value theorem. So here theta must be 0 less than equals to, I think, yeah, 0 less than equals to 1. This is what we know. Okay, so theta may depend on the x, t, everything. Obviously it will depend on t, but x as well, because this is inside the function. So we have this one. Okay, so now I want to write what is the limit h tends to 0 of this particular thing. Then limit h tends to 0 f of t plus h minus f of t by h is equals to limit h tends to 0 0 1 del f del t f of x t plus theta h dm1 x. Okay, now note that we can again use the fact that as del f del t xt is less than equals to m for all xt belongs to 0 1 tens 0 1 for some n greater than 0, because this is uniformly bounded for some n greater than 0. So therefore we can take the this basically main point is that is as this is uniformly bounded, so then we can do the we can make it make sure that we can use the dominated convergence theorem, and so for that reason we have to consider that like gn is equals to del f del t f x comma t plus theta hn type such things, where hn is converging to, this is function of x, where hn is converging to 0, like the previous we have done. Where hn converges to 0, then we have to do this, and in that situation these gn function are actually uniformly bounded because there is m. So then one can use the dominated convergence theorem. So I hope it is clear that. Then using dominated convergence theorem, then using dominated convergence theorem, we get d dt 0 1 fxt dm1 0 to 1 x t dm1 x. I think this is what we have to prove, right? Yeah, this is what we have to prove. So this is done. So this completes the proof basically. Okay, so this is all. So now next go to another problem. In each of the following case, cases, check the function f for Lebesgue integrability over indicated domain. So what is the first case? F of x is equals to 1 plus 1 by x square on R. Second case is that f of x is equals to 1 by x on 0 1, and third is that f of x is equals to 1 by x sin 1 by x on 0 1. So let's do the first. Okay, so here it is asked for the Lebesgue integrability. Okay, so by any we have to show in some way that this is Lebesgue integrable. So what we know is that if a function is, so what you can write theorem, let f is a function from x to c be remain integrable function, be a remain integrable function integrable function, then it is Lebesgue integrable, and integration of the function f over x. Suppose this is real valued function. F or dm1 is equals to integration, or one can write it as let each and subset of R be a measurable set. Lebesgue measurable here. This is equals to f. You don't need this one, so I can give it as a range. This is same with the corresponding Riemann integration. Okay, this is what it is. So now using this fact we will be prove that if a function is, so what we say, if a function is Lebesgue integrable, then it is Riemann integrable, right? Sorry, if it is Riemann integrable, then it is Lebesgue integrable, and the value is same. But value maybe not always needed, but this fact is needed. If it is Riemann integrable, then it is Lebesgue integrable. Okay, that we need always. Okay, so let's first do the first one, that f is a function from real number to real number. This is on real number, I think. Yep. And f of x is equals to 1 plus x square. Okay. So this is what we have given. So then note that integration over R, that is Riemann integration, f of x dx this m1. That we can be written. Why you can write that one first of all? Because you know that characteristic function xn, that is n to n, this characteristic function for every natural number n belongs to natural number, this converges to the constant function 1. Okay, so that means this will converges to the function uh, as n tends to infinity. So this is what we will have. So that therefore we will have this one. So now if we have this one, note that is Riemann integrable on minus n to n for all n belongs to natural number. Okay, so that implies, the Lebesgue integration of this function d mu x is equals to The Lebesgue integration of this is equals to integration minus n to n 1 by 1 plus x square dx, which is equals to 0 to n 2 times 0 to 1 n 1 by 1 plus dx, which can be written as 2 into tan inverse x and 0 to n, okay, which can be written tan inverse 0 is 0, so 2 times tan inverse n, right? 2 times tan inverse n. Now as n tends to infinity, now limit n tends to infinity integration minus n to n dm1x, that is equals to limit n tends to infinity 2 times tan inverse n. Now note that if tan n tends to infinity, then tan inverse n, because that is continuous function, that will go to the 2 into pi by 2, that is equals to pi. So that is finite basically. This is what I need, finite. So therefore, this limit exists finitely. So therefore, f is integrable. F is similarly, one can prove that second one is also integrable. Similar to the above, similar way as it was in above, as it is in above, one can show that 1 by x, so that integration dm1 is f is Lebesgue integrable by using the fact that f is zero one Lebesgue integrable. Okay. Note that I can give a little hint that integration over 0 1, or one can write it as integration over 0 1 1 by x d m1x. This can be written. We can break it first. 0 to 1 by n. Yeah. 0 to 1 by n. That is open interval. Note that this is remain integrable. This fact is remain integrable. So therefore, this fact is remain integrable. This fact is remain integrable. This fact is remain integrable. So therefore, as this is remain integrable, this will be equal to the this will be equal to, then what it will be? That will be log of x, right? Log of mod x. This is x because x is on the and 1 by n to 1. So log 1 is 0 minus log of 1 by n. So that means log of n. Now n tends to infinity. This will be infinity, but integrable. No, this is finite. No, this will not be integrable. This will not be integrable. This will not be. So let me do this. Note that we have this one. Okay. Now now 1 by fx equals to 1 by x on 1 by n to 1 is remain integrable, and integration over 1 by n to 1 by x dx is equals to log x on 1, that will be minus log n. Okay. Minus log plus log n. Okay. Log 1 0 minus log of 1 by n, that is plus log n. So this tends to infinity, plus infinity basically, plus infinity as n tends to infinity. So therefore this limit does not exist finitely. Then fx equals to 1 by x on 0 1 is not integrable, not Lebesgue integrable. So this is integrable means Lebesgue integrable. Okay. So now similarly one have to show that the other one, third one, what it is, third one, that here fx is equals to 1 by x sine 1 by x on 0 1 basically, right? Now let's similarly break it. 0 1 open interval, that is equals to mod of 1 by x. Here it can be plus and minus. Above things always the plus, so that's why the above in above functions their values is always plus, so that's why we don't need to take the mod value. Because main point is that a function will be integrable if mod of ff d m1 is finite. But if f is positive value, then it is enough taking f instead of mod f. Okay. But here function as it is involved sign, so that can take value negative. So that's why you have to take the mod value. Okay. And this one can be written as, we are breaking this 0 1 interval into many intervals. Okay. N equals to 1 to infinity integration over pi n n pi pi by 2 to n pi plus 1 by n by, sorry, 1 by n pi plus pi by 2 to 1 by n pi plus pi by 4. Okay. So what is the issue? Okay. Issue is that you have 0 1 interval. Okay. But here we are not taking the full interval. Here we are not taking full interval. So basically, think that we have 0 1, 0 1. We have taken very small sub intervals. but not taking all the subintervals, okay, which is constituting 0, 1, but taking disjoint. Note that 1 by n pi plus pi by 2 to 1 by n pi plus pi by 4, disjoint n equals to 1 to infinity, are disjoint intervals in 0, 1. Okay, so this you can keep in inside. So but the above thing is actually, but this thing is actually greater than is equals to summation of n equals to 1 to infinity n pi plus pi by 4 whole into 1 by square root of t 1 by n pi plus pi by 4 minus 1 by n pi plus pi by 2. Okay, so basically what we are getting here actually, we can cancel out and we can do whatever we want, but after that what will get, okay, note that sine 1 by x mod is greater than is equals to 1 by square root of t, x less than equals to 1 by n pi plus pi by 4. Okay, whenever x is, okay, so now from here I will not prove this one. So now, so that this is greater than is equals to, for some constant c. So then if you can show this, then it will be done, but you have to show, otherwise there will be a problem. So this is all. So now we'll be doing another problem. So I'll take a little break. Okay, so now the another problem is that show that the dominated convergence theorem. Last problem is problem number 6. So now it is problem number 7. So that the dominated convergence theorem let x s mu be a measure space. Okay, so that the dominated convergence theorem is true if we replace Fn converges to F almost everywhere by Fn converges to F in measure. So that means what we have to prove. That means what we have to prove is that is we need to prove that is we need to prove that if Fn converges to F in measure, if prove that if Fn converges to F in measure, if Fn converges to F in measure, uh, and there exists an integrable function integrable function g on x such that mod of f of nx less than equals to g of x for all n belongs to natural number and for all x belongs to capital X, then integration, then limit, then f is integrable, and second is that limit n tends to infinity, integration mod of fn minus f d mu is equals to 0, or equivalently the particular limit n tends to infinity integration fn d mu is equals to integration f d mu. This is what we have to prove. Okay, first of all, it is known that if fn converges to f in measure, then there exists a subsequence. There exists a subsequence f of nk k equals to 1 to infinity, such that f of nk converges to k f pointwise almost everywhere. Everywhere, okay? Pointwise almost everywhere as k tends to infinity. Okay, this is what the fact. Okay. Another thing is that pointwise almost everywhere. This is the thing. So now we can say that fnk integration fnk d mu converges to integration f d mu. There is no doubt, but we have to use some different things actually. Okay, because we need the limit convergence, not the Okay, convergence pointer is almost everywhere. Then note that Fato's lemma, I think, yeah, Fato's lemma says that for a sequence of measurable functions, measurable functions, for a sequence of measurable functions fn, what you can say is that mm, integration limit infimum n tends to infinity fn d mu is less than equals to limit infimum n tends to infinity integration fn d mu. This is what it is. Now integration x f d mu. I have to prove that integration f is integrable. There is no doubt about this. Note that clearly f is integrable by applying dct on k equals to 1 to infinity. Okay, we can apply dct on f and k equals to 1 to infinity. Okay, then we will be getting that this is integrable, but because there is the g is also there, everything is there. Okay, so now we have to prove that no, not only the subsequent, I mean integration of the limit of the integration of the subsequent converges to integration f, but rather than the full limit will converge to the full limit will converge to the fn. That is what we have to prove. I mean here it is says that okay, I can first of all I can, okay, 1 minute. Let me take it little down. Yeah. So now by using dominated convergence theorem on the sequence, we get f is integrable, f is integrable, and limit k tends to infinity integration over f n k d mu is equals to integration f d mu. Okay, this is what we can write. So now, but also by using Fato's lemma, what we can write, this is the Fato's lemma in general. So therefore, integration over x, but my claim is that 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 not only this particular subsequence converges, but rather it is the full that integration f n d mu converges to f integration f d mu. So let f d mu, this is equals to integration f limit infimum f nl nk, that we can write d mu that is less than equals to, here you are using Fato's lemma, limit n tends to infinity, limit infimum n tends to infinity f of nk x d mu. Okay, so this is always less than equals to limit supremum . Ah, I have to do little different. Little different I have to do. Yeah, what we have to do that we need to show that so that f is integrable, which is easy actually. In fact, we will look at it, and for every subsequent and integration over fx fn d nu n equals to 1 to infinity converges to integration x fx d nu. This is what we have to show. So enough to show that for every subsequence f of nk has a subsequence convergence, has a further subsequent converges to this is what we have to show. Okay, first of all, as if as fn converges to f in major, then any subsequence k equals to 1 to infinity k equals to 1 to infinity will converge to in major, will converge will converge to f in major. Okay, this is the first thing. Then any subsequence f and k equals to 1 to infinity will converge to f in major. This is the first thing. Then there exists subsequence. Then it is known. Then exists a subsequence f n k l l equals to 1 to infinity. That converges almost everywhere. Subsequence that everywhere pointwise to F. Then using DCT to the sequence, because note that here we have the bounded uniform boundary is there, G is there and G is integral, that is there. Now also note that then applying DCT to the sequence, we get F is integrable, first place, and limit L tends to infinity, integration f n k choose L d mu is equals to integration f d mu. So therefore, every sequence has, therefore, every subsequence of 1 to infinity has a further subsequence which converges to integration x f d mu. So this completes the proof. Okay, so I have very less, around 5 to 6 minutes. So what else we can do? Let me little check. If any short, I will in the next problem I will not say much. I'll just next problem I'll start. I don't know how much I'll be able to solve Let f from 0 to infinity, I think this is problem number 8. Yep, problem number 8. Let f from 0 to infinity be uniformly continuous if f is integrable so that limit x tends to plus infinity f of x is equals to 0. If not, if not, so if limit x tends to plus infinity f of x not equals to 0, then there exists an epsilon greater than 0 such that, and there is an epsilon greater than 0 and a sequence. So that means for every sequence there is an epsilon greater than 0 such that for every sequence Tn belongs to 0 to plus infinity with Tn tends to infinity, we have f of Tn epsilon. So this is what it is by not. If limit x tends to infinity fx not equals to 0, that means there is an epsilon greater than 0 such that for every Tn sequence, for every sequence which converges to infinity, ftn will greater than equals to epsilon for all, I think for all n, okay? So, but as f is uniformly continuous, for any epsilon greater than 0, there exists an delta greater than 0 such that whenever x and y belongs to the real number, I think, yeah, belongs to 0, 1, this one with x minus y less than delta, then we should have f of x minus f of y less than epsilon by 2, less than epsilon by 2, yeah, epsilon by 2, we should have this one. So that means whenever x and y, that is that is for any y belongs to Tn minus delta by 2, Tn plus delta by 2, this interval, if it belongs to this interval, then f of y should be greater than equals to epsilon by 2. And this is true for every n, for all n belongs to natural number, and here is also for all n belongs to natural number. So this happens. Now integration over 0 to infinity f mod f d mu, okay, this must be greater than equals to n equals to 1 to infinity. We are just taking some subsets. What is the subsets? The Tn minus delta by 2, sorry, this is delta, this is not delta by 2, this is just delta, epsilon by 2 is taken, delta Tn plus delta, this one with mod of f d mu. Okay, this one. But each of them greater than equals to epsilon by 2 on this particular interval for all n. So that means this must be greater than is equals to n equals to 1 to infinity epsilon by 2. But this series actually goes to infinite. Okay, but this is equals to infinite. So that means that is f is not integrable. This is a contradiction. So fn must, so limit extends to, so we must have limit extends to infinity f of x is equals to 0. I think this is what we are contradicting. Yep. Plus infinity, that doesn't matter because we are completely in the plus infinity set. Okay, so this completes the proof. So this is okay. I'll stop here. And the next day will be mainly focusing the Italy covering theorem and all those things. Okay. Thank you everyone.